So you see here that the geopotential height contours are kind of bent like a ski jump or a skate ramp. And so that's how you can think of these troughs. It's just like a skating ramp. The winds go through the ramp, they accelerate toward the base of the ramp, and then they eject into the other side of the trough, other side of the ski jump. And that other side of the ski jump is where you want to be for your highest chance of robust severe weather. That is called the exit region of the trough. So if we were to draw an axis from the center of the trough through the base of the trough, so basically through the base of the ski jump, we would want to be on the right side of the axis. So all this area over here on the right side of the axis is the exit region of the trough. And the exit region of the trough is the most favored area within the trough for upward motion or lift. Lift is maximized in the exit region of the trough. Lift is one of our most important ingredients for severe weather. And again, in the exit region of these troughs, that's where lift is maximized. And so the exit region of these troughs is where the chances for severe storm initiation is greatest because the lift is maximized in that portion of the trough.
Getting home alive is the goal. That's why these rules matter. Free ebook link in description.
Now, which way the trough is oriented is also important. What happens in the mid and upper levels of the atmosphere, 500 millibars is considered the mid levels of the atmosphere. What happens at these levels dictates what happens in the low levels of the atmosphere. And the orientation and geometry of troughs can give us an idea of how robust the response is going to be at the low levels, because whatever happens in the mid and upper levels of the atmosphere dictates what happens in the lower levels of the atmosphere. So going back to our trough axis here, this dashed pink line basically through the center of the trough down through the base of the quote-unquote ski jump. When this axis is tilted back to the left, like it is here, this is called a negatively tilted trough. Negatively tilted troughs tend to produce a more intense low-level response, which means a more intense surface low or low-level cyclone development. These troughs tend to induce surface low development, especially when they go over the higher terrain areas like the Rockies. So when these strong winds go through the base of the trough and go over the higher terrain of the Rockies, they tend to induce surface low development, surface low pressure development. When you have a negatively tilted trough, that surface low pressure development tends to be more intense than a positively tilted trough, which is when the axis tilts toward the right. So in this example here, we have a very robust trough across the western U.S. Its axis here goes from basically northern Nevada down through the desert southwest into western Mexico. It's tilted back toward the left, so this would be a negatively tilted trough. So we would expect, as this trough moves into the central U.S., that we would see pretty robust surface cyclone and low-level cyclone, low-pressure development in the low levels here in the exit region of that trough. And low-pressure development tends to occur in the exit region of these troughs. So to summarize, at 500 millibars, we want to be looking for these troughs in the geopotential height contours, and we want to focus on the exit region of these troughs for the greatest chance for severe storm initiation because lift is maximized in the exit region of these troughs.
Remember to check out those links in the description below, and then watch another video.